Okay, so first we will review the theorem about the circles, and we will emphasize on the converse. Okay, so the first and the most important theorem is the inscribed angle theorem. Consider a circle and 2 points. Center. And a point on the circle P. And we connect. Okay. The theorem says that this inscribed angle, no matter where P is half of the central angle. Okay, let's consider another situation. What happens if we move to a point Q? Compare angle APB, angle AQ. Okay, so these two angles, which one is bigger? This angle and this angle. Peter, let's turn on the camera. Peter. Okay. So this one is on the circle. We call it the inscribed angle. This one is outside of the circle. Could we compare these two angles? Which one is bigger? Which one is smaller? Oops. Aaron, what do you say about these two angles? Which one is bigger? Or are they the same?
I said the same.
Uh, let's check. So this one, if we add these three angles, we get 180. This one, we add these three angles, we get 180.
Mm.
Now you can see this angle is smaller than this one. We're missing, it's part of it. This angle is smaller than this one. We're missing this part. They add up to 180. They add up to 180. But these two are smaller, so this one must be bigger. So the observation, if the point is outside of the circle, then this angle will be smaller than the inscribed angle. Let's go to the other direction. Let's label this point PQR. Angle.
Question?
Yes.
You said greater?
Uh-huh. So
Oh,
this angle is greater than this one. Why, Aaron?
because there's a gap between P and Q.
Okay. Not only that, more precisely, because if we add this angle, this angle, this angle, what do we get?
AQB.
If we add these three angles, this is the triangle. What's the sum of three interior angles?
Wait, that's an interior?
This triangle, AQP, AQB.
Uh-huh.
If we sum these three angles, we get 180.
Mm-hmm.
Now for this triangle, if we sum these three angles, we also get 180.
Mm-hmm.
However, this component is smaller than this one.
So you're saying that APB has greater angles than AQ?
Yes. Uh-huh.
Huh.
Next, so APB go ARB. So these two angles, which is bigger, which is smaller, or are they equal? Jessica, what do you think?
Wait, I couldn't hear the question.
So angle APB, APB, angle ARB, these two angles,
Mm,
which is bigger, which is smaller, or are they the same?
I think they're the same.
Okay, so you can see this seems to be narrower than this one. It's even more narrow. If we can go a little bit further, the further we go, the smaller the angle becomes. The closer we stay, the bigger the angle becomes. So this time APB is less than, okay, let's use a different color. Why? Okay, let's check proof. We will apply the interior angle theorem. Angle APB, angle PAB, angle PBA, angle AQB. Okay, Kira, what's the sum of these three angles?
180.
Why?
Because they're the interior angles of a triangle.
Okay, the interior angle theorem tells us this is 180. Amy, what about the second one?
It's also 180.
Okay, and these two angles are what we wanted to compare. Aaron, let's check these two angles. Which one is bigger, which one is smaller? PAB, QAB.
PAB.
PAB is,
The interior angle of APB.
so which one is bigger, which one is smaller?
PAB is bigger, QAB is smaller.
QAB, it's this angle, QAB.
Oh, wait.
PAB is this,
Oh, there's a kind of a conflict here, but I'll just say PAB is bigger.
this is PAB, right? This is the QAB. Which angle is bigger? PAB and QAB. You can see QAB is bigger than PAB because it has an extra angle, QAP.
That's why I said.
Okay, so this is bigger. And PBA, PBA, QBA. Again, QBA is bigger. So they all add up to 180. But this one has two smaller components. So this one must be bigger. Otherwise, we won't get 180. In this way, we checked if the point is outside of the circle, then this angle is smaller than the inscribed angle. By the same argument, you can check this angle must be bigger than the inscribed angle. Now you can see when point moves in and out of the circle, this angle changes. Moving out, angle becomes smaller. Moving in, become bigger. It's the inscribed angle exactly at the boundary. Okay, so this allows us to state the converse of this inscribed angle theorem. Let P. Okay, let P be a point on the same side of the chord as the center. So we have a chord, center. We consider any point on the same side as the center. Maybe here, maybe there, as long as it's on the same side. Let me extend this line. Oops. As long as this point is on the same side, if we have the following property, if angle APB if the inscribed angle if this we don't know what initially we don't know where this point is. We only know it's on the same side. With this information, this angle is half of the central angle, then it must be on the circle. Let's compare the two statements. The inscribed angle theorem if P is a point on the circle, we have this property. Now we go backward. If we have this, then it must be on the circle. Because if it's outside, this will be smaller. If it's inside, it will be bigger. If we have this identity, it must be on the circle. Okay. Next, we have this opposite angle theorem. Consider a circle and a quadrilateral. A, B. Okay, such a quadrilateral is called a cyclic. And the opposite angle theorem for cyclic quadrilaterals is that summation of the opposite angles summation okay, this is the opposite angles theorem. These two opposite angles, if this is cyclic, must be 180. Sum of these two angles, if this is cyclic, must be 180. Okay, now the opposite of this is also true. If we have a quadrilateral with one identity here, it must be cyclic. Again, we go backward. The theorem that if we know it's cyclic, we have the identity. The converse is if we have the identity, it must be cyclic. Okay. Next one is the intersecting chord theorem. I'm going to draw a pair of intersecting chords. Label them A, B, C, D. Amy, can you recall the theorem for us?
It's the AE times BE equals CE times DE.
All right, yes, thank you. The theorem says that the product of the two parts, AE and BE, with CE and DE. So if we have two intersecting chords of the same circle, then the product must be the same. That's the intersecting chord theorem. Now let's think, what's the converse? Aaron, could you guess what the converse will be? Let's see if it's reasonable.
If AE times BE equals C times DE, then the circle is proper.
Okay, it's on the right direction. On the right direction. If we have this, then these two chords
Make a circle. I mean,
are on the same circle.
uh-huh.
Okay, yes. So now we know how to state the converse. So if A, E, B, E, C, E, D, E.
Question? What's the
Yes,
point of this converse thing? I just want to know.
converse is so there are different this is something from logic. You have this converse. Have
Wait,
this inverse. Have you seen this before, Aaron? Inverse.
like in functions?
Okay. Yes. So in function, we have inverse function. Okay. So they are kind of going backward, but there are different ways to go backward. Converse, you can think of it as backward. Backward implication.
Mm-hmm.
Backward. For example, here, this implies this. If they are the chord of the same circle, we have the identity. That's the theorem. We go forward. The converse is go backward. If we have the identity, then it must be on the same circle.
Okay.
Then A, B, and C, D chords of the same circle. Okay, so you can see how this goes. Initially, the theorem is going this way. The converse would go this way. If we have the identity. It must be on the same circle. Okay, a few more practice. The tangent line theorem. O A N. Okay, let L be a tangent line. Okay, Kira, do you remember what this theorem states? Tangent line
Like,
theorem. Uh-huh.
not really, but like I know A is like the only point where the tangent like meets a circle.
Oh, okay.
Was it like OA is perpendicular to the line?
Yes. Okay, then OA perpendicular to L. Okay, now let's think about it. What's the converse? Jessica, are you still here? Just okay, Jessica. So let's try. Could you give me the converse of this theorem? What will be the assumption? What will be the conclusion?
Um, well, if it's perpendicular,
Uh-huh. Then it must be
uh, um, uh, right, that,
okay.
I
So I
don't know.
will write down the first part. The converse is if we have a perpendicular condition. If OA is perpendicular to L, then L is okay. Jessica, let's finish. What L must be?
A tangent line of the circle.
Yes, it's a tangent line of the circle. So this time we all go backward. Initially, if we know it's a tangent line, we conclude must be perpendicular. Now the converse, whenever we have a perpendicular intersection, then this line must be a tangent line. Okay, let's try another one. Tangent secant theorem. Let's check with Peter. Are you here, Peter? What about Fred? Can you hear us, Fred?
I can.
Okay. Yeah, okay, let's turn on the camera. Okay, Fred, could you recall what this theorem says? The tangent secant theorem. I'm going to draw a circle.
Repeat it again.
Okay, give me 1 second. Let me
Okay.
draw the setup. So we have a tangent. We have, okay, so let's label this P, A, B. Okay, Fred, let's turn on the camera. Okay, the question is, what does the theorem say? What is the tangent secant theorem about this secant and tangent?
Secant theorem.
Are you in a class? Okay, so it tells us PA squared is the product BB and PC. Okay, so this is the tangent secant theorem. We have a tangent, we have a secant, then this square equals the product PB with PC. Okay, Amy, let's try. What's the converse?
Mm, uh, P PB over PA equals
Okay, so let's see. How do we construct a converse? The
Like
converse
backwards.
So what's the forward? Forward is this, a tangent, a secant, we have the identity.
Oh, I think I have it.
Okay, Aaron, what would you say?
All right. This is just a big shot, but okay.
Uh-huh.
PA squared equals PB times PC. Then uh, PA is a tangent line.
Okay.
Was it right?
Yes. So the forward, the backward. Tangent secant theorem. If we have a secant and a tangent, we have the identity. Now, if we have the identity, then this PA, this square part, must be a tangent. So go forward, now we go backward. So backward is our converse. Let's see another one. Intersecting secant theorem. Okay, Kira, can you recall what this theorem tells us? Secant.
Not really.
Okay.
Yeah.
Think about it. Of this picture, what can we see from this picture? Amy, what do you see?
Is it like I don't know, maybe I mixed it up with another one, but maybe it's like the triangles being similar.
Okay. So a key step for the proof is that these two triangles are similar. From there, we conclude the PA and PB. PC, PD. So how to prove this? We check that the sides have the same ratio. Okay, so proof. This is the same as PA over PC. D over PB. So to prove this, we wanted to check the two triangles, PAC, PDB. Okay, so you did this in the homework. This is the proof. Now let's go the other way. What's the converse? Okay, so again, make a comparison. If we have two secants of the same circle, then the two products, PA times PB, PC times PD, must be the same. Okay, now let's try to construct the converse. What does converse say? What will be the condition? What will be the conclusion?
You could say if PB and PA equals PC and PD, then
Uh-huh.
thing.
If PA, PB, PC, PD. Okay, then P, then AB and CD. Secants of the same circle. Maybe I should say PB, PD is better. Better use PB and PD. P, P. Okay, still we for this one, initially, we don't have the circle. We only have two lines, 4 points. If we have the product, then there's a circle. That is the secant of the same circle. So now let's see, we have constructed the converse for most of our theorems. I'm going back. The inscribed angle theorem, it's converse. The theorem says that if P is a point on the circle, then the inscribed angle is half of the central angle. The converse, if we have the half of the central angle, then this point must be on the circle. Next one, the opposite angle theorem. If we have a cyclic quadrilateral. Summation of the opposite angles must be 180. The converse, if we have two opposite angles add up to 180, then this quadrilateral must be cyclic. And see the theorem and the converse. Then the intersecting chord theorem. The theorem, if we have two chords of the same circle intersecting at E, then the product must be the same. The converse, if we have the same product, then they are the chords of the same circle. Okay, one way, other way. Tangent line theorem. If L is a tangent line, then this must be perpendicular. The converse, if this is perpendicular, this line must be a tangent line. So we can go back and forth. Tangent secant. So this statement can be improved. Maybe later after we show how to draw the circle containing any 3 points. We'll visit this later. And intersect and secant theorem, similar. Okay, so many of the theorems we learned in the book, in our class, initially it goes one way. Two secants of the same circle of equal product. But in many cases, goes the other way. If there's equal product, then they are secants of the same circle. Okay, so we will have 5 minutes break and be back at 8:19.
Okay.
Okay, 5 minutes break. Okay. Then let's recall the definition of concurrency. Concurrent line. Three lines, so they are concurrent. Okay, I draw a picture. One line, second line. Now when we draw the third line, we should be careful for them to be concurrent. They must go through the intersection point. Okay. the first application of this is the angle bisectors. Theorem. Any triangle A, B, C. We can draw the angle bisector. Angle bisector. Okay, theorem. Okay, the theorem for any triangle, we can draw the three angle bisectors. But initially, they may be quite arbitrary. However, the theorem says they are concurrent. They intersect at the same point. Let's recall how is this proved. Have you seen this property before? In our homework. In our homework 14, we showed that if we draw the angle bisector, we label this point, we connect A and this point, we should this also bisect the angle. In particular, the three angle bisectors are concurrent. So let's recall. That's how we proved that the three are concurrent. We start with two of them. These two angle bisectors will intersect at common point. Now we connect this with the third, and we prove this is also a angle bisector. Therefore, the three angle bisectors intersect the same point, so they are concurrent. And to prove this, I'm going to draw another. I'm going to copy the graph here. Make a copy. Oops, that's too bad. I'm not sure if this refresh your memory of our homework. In our homework, we find the intersection point. Oh, sorry, the intersection point. Then we draw three perpendicular lines. This one, and this one. We showed that these two triangles are congruent. These two sides, same length. These two triangles congruent. These two sides, same length. In particular, the three are same length. Then we show these two triangles are congruent. Therefore, the two angles are the same. This is the angle bisect. That's from our homework. So we will call this I. And previously we called it P. Later you will see why we change it to I. We call this E, F, G. So in our homework we showed so we denote the common value as R. Then we can draw the circle center at I with radius R. Draw circle. Okay. So we first find the intersection of the three angle bisectors. Then we find the distance because they are all the same. If we draw the circle of radius R, it will go through all 3 points. It's easy to see. The interesting thing about this is not only it contains the 3 points, this circle is actually tangent to the 3 sides. Moreover, 3 sides.
Tangent to the what?
I haven't finished yet.
Oh.
Let me rewrite this time. Okay. Initially, we only know the circle contains the 3 points because it's equal to the radius. It's equal to the radius, so E, F, G must be on the circle. Now we want to say a little bit more. Not only they are on the circle, they're also the tangent point. Why? There must be a tangent. So I'm going to roll back to the previous page of our converse of the tangent line theorem. The tangent line theorem, if this is the tangent, it must be perpendicular. But the converse, if this is perpendicular, it must be tangent. So we will apply the converse of the tangent line theorem. Okay, I'm going back to where we are now. Why are they tangent? Because it's perpendicular, perpendicular, perpendicular. Find the converse. Tangent line theorem. since IE perpendicular to BC, it implies BC is tangent. Okay, any question about this step? Why there must be tangent? Aaron, questions or no? Okay, now let's see. What about AC? Why must be a tangent?
I have a question.
Yes, Aaron.
Can that last sentence be applied to IF and IG?
Well, okay. So that's what I'm going to ask you. Why AC must be tangent to the circle? Aaron, what's your answer?
Well, IF is perpendicular to AC.
Okay. And Amy, why AB must be a tangent?
Because you could say they're like converse.
Okay.
Like,
So because we know this is the perpendicular, then by the converse of tangent line theorem, AB is also tangent to the circle at G. Okay, so the same argument works for BC, AC, and AB. Okay, I will let you finish this. AC, 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 we get F, AB, AB is tangent to the circle at G. Okay, you can finish this after class, so I'm not going to repeat all of this. Okay. Then last time we also showed how to find the length of the smaller segments. Okay, so we will label this BC is the opposite side of angle A. We call this lowercase a, lowercase b, lowercase c. The length of the three sides. To find the length, I will call this x, because we showed that these two triangles are congruent. So this x, this also x. These two sides, same length, because the triangles are congruent. I'm going to label this x, label this y, label this z. Let's choose a different color. It's too many letters. I'm going to use okay, too many. So I'll call this x, y, z. Okay, next we will recall how to find the three variables x, y, z. Could I copy this? Let me try.
What happened?
I'm going to make a copy over here because we are moving the, okay. Okay, so the same graph. So now we want to set up a system of equations about the unknowns. We start with x plus y. What is x plus y? X plus y. This gives the side AB, which is our C. Then x plus z. X plus z is AC, which is our B. Similarly, y plus z is our A. Okay, so we have three equations about the three unknowns x, y, z. Okay, let's recall how did we find them last time?
You had to be given a number for C, B, and A.
So these are the parameters. It's the three sides. This you can view this as a known. We know A, B, C. We want to find x, y, z.
X equals B minus.
Okay, so eventually we want to get find all of them. So, but first, let's add the right side together. What do we have? If we add this, what do we get, Aaron?
2x plus 2z plus 2y equals
2x, 2y, 2z. If we add them, it should be the sum of this. Okay, so add together three equations. Okay, Aaron. 2x, 2y, 2z equals A, B, C. And this is the perimeter, which is twice of the half perimeter.
That's 2s.
Okay, we divide by 2, we get x plus 1. Z equals S. Okay, nice. Now we're going to find the three unknowns. X. From the last equation, x is S minus y plus Z.
Y plus C.
Which is
S minus A.
S minus A. And Y. Jessica, how do you find Y?
S minus of z plus x equals S minus B.
Okay. And Kira, how to find the Z?
S minus x plus y. Well, which is x minus c. S minus c.
Okay. So in this way, we find all three of them. Okay. Next, we want to find the radius of this circle. Okay. I'm going to make a copy of this again. Oh, I cannot move it across the page. paste. Okay, nice. Okay, so I'm going to erase many of the something we don't use anymore. Because there are too many letters. Oops. We have this A, B, C, E, F, G. I want to find the area of the triangle. We start with BIC. Amy, we have a triangle BIC. How could you give me a formula for the area of this triangle?
You can do, wait, let me recall it. S
Uh-huh.
times square root of, wait, no. Square root of S times
Okay. So
something like that.
that will be the Heron theorem. Is if we know the size of all three sides, then we can find the formula. So here it's a little bit simpler. We have the height and the base. So the area, Amy, how do you use this information? Height and the base.
You can just like multiply them and divide it by 2.
Okay, so it will be 1/2 of IE base BC. IE is our radius. BC is the opposite side of A. Okay, now let's move to the next area. Triangle AIC. I'm going to check with Kira. Could you give me the area of this triangle?
1/2 of IF times AC equals 1/2. Still 1/2 R times. So it's 1/2 R times B.
Okay, nice. Aaron, the third triangle, area AIB.
1/2 of IG times AB, also known as 1/2 of RC.
Okay, Jessica, if I add all three of them, what do we get? This one, this one, this one. What's the summation of the total area? So this will be the area of the triangle ABC. So if we add them together, 1/2 area ABC. This is 1/2 A. Okay, so this half perimeter appears again. Now we recall the formula you mentioned. So, okay, oops. Okay, Aaron, what's the Heron formula for the area of the triangle?
It's root S times S minus A and then S minus B and then X minus C. Wait, no, I meant S minus C, sorry.
Okay, yes, Kira.
For the area of triangle AIB, it's supposed to be 1/2 IG times AB and not equals.
Okay, yes.
Okay.
I made a mistake. Let me correct it. IG time. Okay, yes. Thank you. Okay, so now we have two formulas for the same area. One S time R. Two, the hidden formula. These two must be the same because both give us the area. This implies SR. So from there, we find the formula for the radius. Because we know that S is the same as square root of h squared. So we can move this to the square root. Which is okay. So we find the radius of the circle. We are going to give a name for this. So this circle is tangent to all three sides of the triangle. We will call it the inscribed triangle. The inscribed circle, I'm not sure what I said before. It's the inscribed circle. The inscribed circle of the triangle. Because we use this so often, we want to give it a shorter name. We will also call it the incircle. The incircle is short for the inscribed circle. Sometimes we will just ignore the dashed line, just write the incircle. Okay, so you know what does this mean? When you say incircle, the new word is actually a short word for the inscribed circle. A circle inside the triangle that is tangent to all three sides. Because of this, we call this radius. The radius of the inscribed circle, we also call it the inradius. Or we just say inradius. Okay. So this is a very important construction. So given any triangle, we can draw the incircle, can find the inradius. And I, the incenter. Okay. We have the inscribed circle. Then we define the inradius of the triangle to be the radius of the incircle. And the center, we call it the incenter of the triangle. So these are properties of the triangle. Given any triangle, we can find the incenter. We can compute the inradius. Then we can draw the incircle. And next time, we will construct a different center. This is the incenter. The next is the center of mass. So for that one, we will need the median. Give a brief introduction. It's similar to the angle bisectors, slightly different. We find the midpoint of this side. Let's label this. Let E be the midpoint. Then AE is called a median. So we can find the midpoint, connect, midpoint, connect. It turns out the three medians are also concurrent. And we will learn more about this next time. Okay, questions about this lecture? Okay, Kira.